Okay, good morning, everyone. So we are very happy to have Elliott Gesteau giving us the first talk of this morning session. Stage is yours. Go ahead.
Okay, hi everyone. Thank you for the invitation and thank you to the organizers for organizing all of this. It's been really fun. So today my talk will be called Failures of Spacetime Emergence, and it will be based on these three papers that I worked on with some of them with Netta and Daniel over the last year or so. And towards the end of the talk, I'll also mention briefly some work in progress with Netta. So one of the most important lessons of holography is that spacetime is not a fundamental concept, rather it is emergent. When we think about the bulk geometry in ADS-CFT, we should really think of it as some form of emergent concept that appears when n becomes very large on the boundary. And some recent development that we've already heard about from a variety of perspectives in this conference is that recently we realized that some asymptotically ADS geometries fail to emerge from the CFT in the way that we previously thought that they would. Of course, this is a vastly underdefined claim because I really need to tell you what I actually mean by fail to emerge. And so this question of what do we mean by fail to emerge will be a significant portion of the talk. We will try to be as precise as we can about what is actually meant by this and in what sense it's different from other situations in ADS-CFT. The first comment that I want to make is that there are usually two languages that we can use to talk about emergence in the context of ADS-CFT. The first one is perhaps the most recent one and the most precise one. It's the language of the large n limits within the context of von Neumann algebras and things like that. And there's also another language that I guess is a bit older, which is the language of quantum error correction. And we've heard talks about both perspectives in the conference already. So we've heard Hong and Jonah tell us about some properties of the large n limit. And on the other hand, we've heard Daniel and Ying tell us some things about quantum error correction. And so part of this talk today is going to be about explaining how these two languages can tell us that in some situations in ADS-CFT, spacetime fails to emerge, how the two languages are related. And then I will also comment on the role of the observer, which seems to be this new ingredient that we need to add in this whole story. And towards the end, I'll propose a unifying picture for all of these failures of emergence based on this upcoming work with Netta. Okay, so how is the talk going to go? Well, the first part, I want to understand the failure of emergence of some spacetimes in ADS-CFT from the point of view of the large n limit. So this is where I will be talking about this first paper that was flashing on the first slide, which is a no-go theorem for large n closed universes. Then I will move on to trying to understand the same types of failure of emergence from the point of view of quantum error correction. And so this is where I will describe it in terms of tensor networks. And we will also introduce observer rules. And finally, I'll sort of try to repackage the main lessons we've learned into one covariant diagnosis of the failure of emergence of spacetime, which we proposed with Netta as the complementarity wedge. Okay, so the first part is about the large n perspective on the failure of emergence of spacetime. It's mainly based on this paper that I put out on the archive in September, and it will also be very related to some of the things that Hong and Jonah told us. So there was this paper by Hong that was coordinated with this paper, and then a few weeks later there was also this paper that Jonah talked about the gravitational path integral, and how we can also understand all of this from the point of view of the gravitational path integral, as he told us yesterday. Okay. So we've heard a few times already in this conference about the AS squared cosmology. So this is a setup that is due to Antonini, Sciascia, and Swingle. And what happens, as we were told yesterday, is that you take a partially entangled thermal state of two CFTs. So this formula here is essentially a thermofield double formula, but you see that in the middle, you've inserted this heavy operator, O. So O in this formula is a heavy operator of dimension order n squared. And very importantly, as we saw yesterday, this was a really crucial point, the temperatures are taken to be below the Hawking-Page transition. So then what you can do is that you can try to prepare this state with a Euclidean path integral. And so the bottom row, the bottom side of this diagram here really represents this Euclidean preparation. So you have these two circle arcs that correspond to the inverse temperature. And then in the middle, you insert this heavy operator O, and you model it as a heavy dust shell in the bulk. And then you solve Einstein's equation. And what you find is that when you continue the solution to Lorentzian signature, so this is the top part of this diagram, The solution is made out of three components. There are two exterior ADS components here. And in the middle, there is this crunching cosmology that is a closed universe. So it's time reflection symmetric. So if you want to think of the whole Lorentzian solution, you would just reflect with respect to this axis here. So that seems like a very interesting setup because it's a setup where it looks like we're preparing a baby universe in ADS CFT. And so if we want to understand the physics of closed universes from the point of view of ADS CFT, it looks like an interesting setup. But a year later, Stefano and Pratik told us that there was a puzzle about this setup, which goes as follows. So in a holographic CFT, there's usually two sectors of energy. There's a sort of integrable sector at low energies, order n to the 0, and the states in that sector are very, the spacing between them is big. It's also order n to the 0, so it's not very densely populated. And then there's another sector, which is the high energy sector, which has states of energy order n squared, and it becomes exponentially populated in n. The degeneracy, the spacings between the levels are very, very small. So what Hawking page does is that it tells us which of these two sectors win. And below the Hawking page transition, in particular, the sector that wins is the order n to the 0 energy sector. So this is the sector that dominates. And essentially, in this sector, the states, because it's supported mainly on eigenstates that have order n to the 0 energy, can be thought of as a finite excitation of two copies of the vacuum, because we can truncate it to a very large, but order 1 size microcanonical window. And to good approximation, the state should live there below the Hawking page transition, like it is in the case of AS squared, at least in some regime of parameters. But now such states that are finite excitations of two copies of the vacuum are really the simplest ones in ADS CFT. Those states are just, the vacuum acted on by finitely many light fields. And so from just the most basic application of the extrapolate dictionary, what we would expect is that these states are just dual to two entangled copies of ADS with some light fields entangled, but that there would be no closed universe to be seen. So in particular, when we look at the state from this perspective, it looks really strange that there is a closed universe in the bulk. So that's the puzzle. Is the closed universe emergent or not? Should we trust this story or should we trust the gravity computation? Well, this is the first time that we are mentioning the word emergence in this talk, so I want to take some time to define the notion of emergence from the point of view of the large n limit in a way that's as precise as possible. The large n limit is the most traditional and precise way of thinking about emergence in ADS CFT. And we can formulate it as follows. So we're going to suppose that we have a bulk field theory on a given bulk background, and we put it in a state psi. And then we're going to consider a sequence of finite n boundary states psi n. The question is there a sense in which this field theory on this bulk background in a state psi is emergent from the sequence of finite n states psi n? The definition that we can use is that the background is emergent if for all operators O of the bulk field theory that lives on this background that we're trying to see it if emerges or not, there exists a sequence of finite n operators On such that the correlators of On in the finite n state psi n go to the correlators of the operator O in the state psi as I take the large n limit. This is just a mathematical repackaging of the fact that we want to think about emergence in this context as the fact that we can reproduce the correlation functions of all bulk fields from the boundary in the large n limit. Okay, this is just saying that as I take n to infinity, I can find good operators for which the correlation functions in the bulk fields are arbitrarily well approximated by the finite n operators.
Are the open CFT operators?
Yes, yeah, they're boundary operators. Now those CFT operators On can be complicated in general. And I don't want to ask too much of them in general, but there is one case in which they should really be something more. This is the case where the ONs live in the causal wedge of the geometry. If the ONs are behind the causal wedge, especially in something like a Python's lunch or something, we would expect their reconstructs to be exponentially complex. But if they're in the causal wedge, then we know that we can apply the HKLL dictionary to these operators. And so really they should be reconstructed by products of finitely many single trace operators that are appropriately normalized by their one-point function. Okay, this is just the statement of the HKLL reconstruction in the causal wedge. So what we learned from this is that at least if we want to know the large n states of the causal wedge of the theory, We can just do this by looking at large n limits of correlators of single trace operators on the boundary. So now let's try to apply what we've learned from this definition to our case. In our case, the causal wedge is the two copies of ADS. It's these two regions here and here. So the large n states of the two copies of ADS, if it exists, by the definition that we've just given, is determined by the large n limits of correlators of single trace operators on the boundary. Now, if the closed universe is emergent in the sense that the correlators get close to the one that you would expect in this geometry with a closed universe, then that would mean that the large n single trace operators must be in an overall mixed state at large n. This is because the causal wedge here, which has the two copies of ADS, should be entangled with the closed universe in the geometry. So when you trace the closed universe out, you should have those two copies in a mixed state. This is where this no-go theorem that appeared in this paper shows up. So the theorem tells you that if you suppose that the correlators of single trace operators of a sequence of states of order n to the 0 energy, like the AS squared states in the regime of parameters I want to consider today, have a large n limit, then the limit correlators must be those of a pure state on two copies of ADS. In other words, there is no situation in which those single trace operators will have a large n limit, and the correlators of the large n limit will be consistent with there being a mixed state in the two copies of ADS. And from this, we can rule out the possibility of the emergence of a closed universe in this two-sided geometry. So I just want to give you a brief idea of the proof. The first step is to write the finite n states as a linear combination of the finite n energy eigenstates. So these CABNs here, they're just the Boltzmann suppression factors multiplied by the matrix elements of the operator O. Now, as Hong stressed yesterday, there is no reason why these CABNs should be independent of n. They can be n-dependent in general, and actually we expect them to have this erratic n behavior. So the first step of the proof is to get around that by extracting a subset of integers, phi of n, for which those CAB phi of n's all converge toward a finite value. This is possible because these CABNs square to a probability, so they're bounded, so they will have an accumulation point. So essentially, this is just forcing all of these CABNs to converge to their accumulation point by extracting a subset of indices. Then once we've done that, we can introduce a new state, which is the same states as the psi n, but where we've replaced these coefficients that have this n-erratic dependence by the accumulation points. And now the crucial step is to show that the single trace operator correlators in the original state with this n-erratic dependence and the new state where I've replaced these n-erratic coefficients by their accumulation points get close. What is this type of question? Well, the idea is that if you want to construct the correlators of single trace operators in these states, you want to sum over the correlator. You will have a sum that will feature these CABNs and then matrix elements of the single trace operators in the energy eigenstates. If we could switch the sum and the limit and just take these CAB phi of n's to their accumulation points, then we would be done. And it turns out that in this case, we can actually switch the sum and the limit. And this is because the sum is essentially finitely supported. It's just supported, that's what we said by this microcanonical window argument. We can think of this sum as morally just being supported on a finite window. So in this case, we can switch the sum and the limit, and that guarantees that those two things get close, at least for this choice of subset of values phi of n. Now the next step is to show that the correlators in this state where the CAB zeros now don't have any n-erratic behavior get close to the ones of a pure state on two copies of ADS. And this is essentially because it's a constant in n finite excitation of the vacuum. And then recall that, so now we've shown that the correlators of single trace operators in these psi phi of n have a limit. And those are the correlators of a pure state on two copies of ADS. Moreover, we've assumed that the whole sequence of correlators of single trace operators also has a limit. So it is sufficient to determine this limit to find a subsequence of the correlators of single trace operators and to find what the limit of that subsequence is. Here we've exhibited a subsequence for which the limit is just the correlators of a pure state on two copies of ADS. So by uniqueness of the limit, we can conclude that the correlators of single trace operators in this state have a limit which is the the correlators of a pure state on two copies of ADS. Now I want to make a few comments on this proof. The first comment is that this proof would completely fail at high temperature. The reason why it would fail is that in this proof, recall that the crucial point was that we needed to consider two states, the states where these CABs have some n-erratic behavior, and the state where these CABs don't. And we were able to show that the correlators of single trace operators in these states are close only because they were mostly supported on a fixed microcanonical window of finite size. At high temperature, this is completely wrong. The high temperature states are not supported on the order n to the 0 energy part of the spectrum. They're supported on the order n squared energy part of the spectrum. This is a part that gets more and more populated as n goes to infinity, and that also gets pushed to infinity. So in that case, at high temperature, we cannot switch the sum and the limit. And in this case, it is actually possible that there are some sequences of states for which the correlators of single trace operators will asymptote to those of a mixed state. And actually, this is what to be expected, because from what Hong and Jonah told us yesterday, at high temperature, the analog of the state of the AS squared cosmology is just a long wormhole with a throat in the middle. There we expect the exteriors of the long wormhole to have a large n limit, but of course, they will be entangled to the interiors of the long wormhole, which is the throat. Okay, so this is why the situation at low temperature and at high temperature, from the point of view of large n emergence, is very different, even in the causal wedge. For those who like measure theory, you can see this as an instance of the dominated convergence theorem, which is this foundational result that tells you when you can switch a sum and a limit. Essentially, it tells you that you can switch a sum and a limit when the support of the sum is essentially finite. So here, this is exactly what's happening. At low temperature, you're allowed to switch the sum and the limit, but it's precisely the failure of the dominated convergence theorem at high temperature that allows you to have correlators that are consistent with a mixed state in the two exteriors. The last comment is that we can show similar results for order n to the 0 entropy. As Jonah said yesterday, this is really the important assumption, and you would be able to formulate similar things here, even though I formulated it in terms of energy in this paper, given that the AS squared situation was the main case of interest. So as a conclusion, for a sequence of states of order n to the 0 energy, either the large n state of single trace operators is pure or it doesn't exist. And then there were these two papers that we heard about yesterday that provided evidence for the lack of existence of a large n limit in the case of AS squared. All right, so this is how I want to think about the failure of spacetime emergence from the point of view of the large n limit. Now I want to move on to the second part of this talk, which is how to see the same types of phenomena from the point of view of quantum error correction, and how we can relate this to the first part, and also hopefully make some more progress about the question. So this is related to these two papers that we put out together in April with Netta and in July with Netta and Daniel. So how should we think about emergence in tensor networks, and how should this compare to the large n definition of emergence? Well, imagine that we have some big holographic map that is a tensor network map that is the kind of map that we would always write when we do tensor network models of holography. I want to be very general here. I just have a map, a linear map that maps a bottom row to a top row. Now I want to try to think about how to think about those different, think about this map in the context of the large n limit. The way that I want to think about this map is that I really want to think of the top row of this map as the fundamental description at finite n. This top row should be your UV complete finite n CFT for one choice of n, no averaging, nothing like that, just one choice of n. On the other hand, the bottom row I want to think of as some form of tentative effective description. Sometimes this effective description will just be the tentative infinite n theory. As we will see later, it's not always possible to exactly say that. And the point is that we're trying to see if this bottom row emerges from the top row. So we're trying to see if there is a way to map this bottom row into the top row that tells us that it can be emergent from the fundamental description. And the rules that are usually used in the tensor network literature is that the bottom row can emerge from the top row only if the inner product is preserved between the bottom row and the top row under the application of the holographic map. And you can reconstruct EFT operators to good accuracy. So this is the statement that you can reconstruct the operators. And you see that the error that is allowed is in both cases exponentially small in n squared. So this is like saying that we can do perturbation theory in the bulk. How is this related to the large N definition? Well, the inner products between these qubits in these toy models are just supposed to encode the correlators of fields in the bulk or on the boundary. So once again, the fact that the inner products gets closed, is exactly the same statement as saying that we want the correlators of finite N operators on the boundary to be able to approach those of the putative picture that we're trying to see if it emerges or not. Okay, so this is just another way of phrasing the same thing. Okay, so with this in mind, we can try to write down a tensor network for the AS squared cosmology. So we have our two regions here. You know, A is the union of the two ADSs, is the causal wedge, and B is the closed universe. And so we have a map that is the tensor network map that inputs some putative semi-classical state psi1 into the map. And we're trying to see if this state can emerge from the fundamental description. So we said that the finite N description lives in the top row. It lives here. And you know, the candidate's infinite N description lives in the bottom row. So the top row, you see, just contains this set of qubits A, which corresponds to the two boundaries. The bottom row contains the qubits in the causal wedge, as well as the qubits in the closed universe here. And we have some entangled state between the qubits in the closed universe and the qubits in the causal wedge. Now we're trying to ask this tensor network if this bottom row, this set of qubits both in the causal wedge and in the closed universe, can emerge from the top row, which just contains the asymptotic boundary. Well, let's first delve into the details of how the tensor network is written down. So the causal wedge first gets mapped isometrically to the boundary. This is just the statement that operators in the causal wedge, as we said before, can just be reconstructed by finite products of single trace operators. So the way that we usually model this in the tensor network language is through an isometry. On the other hand, the closed universe doesn't have any boundaries, so it doesn't get mapped to anything. And the way that we usually explain that is that it gets post-selected after applying a random orthogonal matrix, because the closed universe doesn't have any fundamental description. So yeah, this also could be a unitary matrix in some models. This is a debate that I won't get into today. And then the question is, how does this network that is so constructed know about the failure of emergence that we described in the previous section? How can this network tell us that this tentative bottom row cannot be the large N limit of the top row? Well, we can do exactly what we said. So we can compute, for example, the fluctuation of inner products as I apply this whole holographic map VTN to the state psi1. And what you would find if you did that is that you would find that the fluctuation is controlled by e to the minus the second Renyi entropy of psi1, restricted to the causal wedge. Here, because the state psi1 is supposed to be a state of order 1 entropy, this is an order 1 number. It doesn't go away as we take n to infinity. And so we say that the fluctuation of inner products is not suppressed when you take n to infinity, and hence this bottom row cannot emerge, just like we said the same thing in the case of the large N limit. There is another way that you can diagnose the fact that the bottom row cannot emerge from the top row, which is based on this paper that we put out with Netta in April, which is to do a swap test. So what do? We take two copies of the system. We just copy the system. And we consider the following operator. So here by HA, I really mean the Hilbert space of the two regions of ADS together. And I want an operator that maps the Hilbert space of these two regions, tensor, the second copy of the Hilbert space of these two regions to itself, and that swaps the states that live in these two regions in the semi-classical description. The reason why we like this operator in the semi-classical description is that in quantum information theory, swap is supposed to compute e to the minus the second Renyi entropy of the state. So here, if I have a putative semi-classical state that I'm trying to see if emerges or not, and I compute the expectation value of swap in two copies of this state, I will find e to the minus the second Renyi entropy of this state restricted to the causal wedge. Now, on the other hand, if we do what in this toy model corresponds to mapping this operator which just lives in the causal wedge to the fundamental description by replacing it with a finite product of single trace operators, what we would find is that we just conjugate it with this HKLL map, which is what this is doing in this language. And then we would find that the expectation value of this operator is actually close to 1. So once again, what is this telling us? This is telling us that there is an operator in the causal wedge whose expectation value in the picture we're trying to make emerge is very, very, very small, whereas the expectation value in the fundamental description stays big regardless of the value of n. Once again, these two correlators do not get close in the large n limit. And from the point of view of the tensor network, we see this as a mismatch of expectation values between candidate large n picture and finite n picture, which is a failure of emergence. Okay, so this is how we can think about the AS squared cosmology in a very similar way as we think about it in the large n limit, just in the language of tensor networks. But now that I've written the tensor network for the AS squared cosmology, those of you who worked on tensor networks for black hole evaporation might have noticed that it looked pretty similar. In particular, if you write the non-isometric code that was proposed in this paper to describe black hole evaporation, what do? Well, you essentially do the same thing up to one difference, which is that you have the radiation. So this lives outside the interior. So it's the analog of the two copies of ADS. It's the analog of the causal wedge. It can be mapped to the boundary effortlessly. So it gets mapped through an isometry. Here, the isometry is even just the identity. And then you have the interior modes. So you have the left movers and the right movers. And those you also want to post-select because there's too many of them compared to area over 4G. But the difference is that area over 4G is not zero. So in the fundamental description, you're not post-selecting onto just one state. You're post-selecting onto some states, but then you still have some free legs in the fundamental description. And there's e to the area over 4G of them. This is just because, yeah, the black hole horizon has non-zero area at partial evaporation. So this is the only difference. But if this B leg was not here, it would be exactly the same tensor network as before. On the other hand, at full evaporation, then this is the case where area over 4G goes to zero. So there are actually no longer fundamental description degrees of freedom of the black hole. You can see this geometrically by saying that the Cauchy slice that describes a fully evaporated black hole disconnects the interior from the exterior through the singularity. So you can kind of think of the interior portion as a closed universe, and this is because the area of the horizon has zero size here. And so at full evaporation, if you want to write down the right tensor network to model the situation, it would just really be about removing this B leg and just having this one post selection here. Okay, so this code for full evaporation looks extremely similar to the AS squared code, and we can expect similar results to hold. So we can do the same thing. For example, we can try to test for the emergence of the putative semi-classical description that we want in terms of operator reconstruction, and we can do a swap test again and see what happens. So if we do a swap test on the radiation, which would be the analog of doing a swap test on the two copies of ADS in the previous example, then what we would find is that at partial evaporation, the errors in swap reconstruction are extremely small. They're exponentially suppressed in n squared. And essentially, this is because even though you're post-selecting on some states here, even in the fundamental description, the radiation can still be entangled to some black hole degrees of freedom, and there's a parametrically large number of them. So that's why this error is small. So from the point of view of the swap test, we don't detect any failure of emergence in partial evaporation, which is consistent with the picture that was given in the non-isometric code paper, where people were trying to argue that the interior is still emergent at partial evaporation, even after the page time. On the other hand, at full evaporation, the code is exactly the same as in the AS squared situation, and so the conclusion is also exactly the same. We find an error in swap operator reconstruction that is big. It's of order 1. It is not exponentially suppressed in n squared, and there we once again see a failure of emergence. So here swap signals a failure of emergence only at full evaporation. Okay, now that we've seen that the tensor networks between the black hole case and the AS squared case look so similar, and we've also seen that we can understand the AS squared case from the point of view of the large n limit, it is tempting to try to think about the evaporating black hole case also from the point of view of some kind of large n limit. I think this is possible to do and that this would be really interesting to do, but I just want to point out some interesting subtleties that show up there that I think would be worth thinking about. So in the case of the evaporating black hole, the first problem is that we cannot really think of the bottom row, the semi-classical picture we're trying to make emerge, as a candidate large n geometry. And the reason for this is that really when we want to think of some semi-classical picture that describes the evaporating black hole, the volume of the interior diverges with n. Okay, it's proportional to 1 over g. So in the end, the geometry that we're trying to make emerge is something that very finely depends on the value of n. It blows up at infinite n. In other words, it's not uniquely defined at infinite n. It's more there's one geometry for each choice of n. This notion was formalized, as Hong told us yesterday, as the notion of quantum volatile spacetime in this paper by Netta and Hong. And this is the first subtlety. If we want to make sense of this, then we have to tackle the quantum volatility of the spacetime. There's another somewhat related subtlety, which is that the swap test that we use to diagnose the failure of emergence in the tensor network has a complexity that is not of order 1. It has a complexity that is polynomial in n. This is just because you have order n qubits of radiation. So, if you want to swap them, you have to do something of polynomial complexity. In the AS squared case, because we just had an order 1 entanglement, then you wouldn't have had this issue. Okay, so this is a clear difference. And both of these features are not captured by the most basic construction of large n algebras. Indeed, one large n theory on a fixed background is usually assumed. You assume that there's one large n theory, so no quantum volatility. And also, you usually include in your large n algebra only just finite products of single trace operators. These finite products of single trace operators, as Jonah was discussing in the context of the radiation, would just amount to operators acting on finitely many qubits of radiation. Here we would need a swap test that acts on infinitely many qubits in the large n limit. And it would be really interesting to try to understand how to incorporate these two features into the large n analysis to restore the same conclusions. Yeah, I want to emphasize, by the way, that polynomial in n operations were really included in the definition of emergence in this whole, page curve story. The things that we were allowed to not include to talk about emergence were exponentially complex operations, but we should definitely be able to talk about polynomially complex operations to talk about black hole evaporation. Okay, so speaking of things that don't have a good analog in the large n limits, there's something else, which is these observer rules. The idea is that when a portion of space-time fails to emerge, it seems that we need to introduce an observer. And so Daniel and Ying told us about how to do this in tensor networks through this quantum to classical channel. And essentially, what this amounts to in terms of the holographic map is adding these extra clone degrees of freedom for the observer. So I won't go into the details of the prescription, but the main thing we will need here is that essentially, adding the observer rule is like taking some qubits in the putative description we're trying to make emerge, implementing this Heisenberg cut, and the way that you implement it is by introducing this clone of these qubits that adds some degrees of freedom into your fundamental description. We don't have a good analog in the large n limit of that, but at least what these people told us, and there was also this related rule here, is that the new rule for emergence should be that errors should now be exponentially small in this code for inner products and operator reconstruction and so on, not in 1 over n or in e to the minus n squared, but in the observer's entropy, okay? And so that's our new rule for emergence. It's the same one, fluctuations suppressed, but now in the observer's entropy. And now you can ask, what happens when you apply this rule and you try to introduce observers in different places of the geometry, both in the S squared case and the evaporating black hole case? So in the AS squared case, we can take two observers, alpha and beta. Alpha lives outside the closed universe and beta lives inside the closed universe. And then, for alpha outside the closed universe, we apply the observer rule to some qubits that are supposed to model this observer alpha. And we ask, well, is the situation better? Can we declare emergence of the closed universe now from the point of view of this new code with the rules that I just said? And the answer is no. You still have large fluctuations. You still have errors in swap reconstruction. So from the point of view of the alpha observer, the observer rule doesn't help. The closed universe is still not emergent. But then if you put beta inside the closed universe, then the code is fixed. The errors are now exponentially suppressed in the entropy of beta. Now you could worry, because this sounds like whether or not the closed universe is emergent depends on where the observer is in the geometry. And this sounds very strange. But we found some comfort in the fact that this seems to nicely echo this idea by Saska and Torlasius and Aglom of complementarity, which is that sometimes it is okay for observers to disagree in quantum gravity when they cannot communicate. And here this is exactly the case because these observers live in different connected components of spacetime. The story for the evaporating black hole is very similar. So you can look at two slices, sigma 1 partially evaporated, sigma 2 fully evaporated. On the partially evaporated slice, as we discussed before, because these non-isometric codes essentially work up to exponentially small corrections, there's no failure of emergence for either observer, so you don't need to talk about this observer dependence. But what we found in this paper is that on the fully evaporated slice, as we discussed before, the code now looks exactly like an AS squared code. It's just the number of qubits that changes. And so once again, if you take an observer that stays outside the black hole at all times and another one that jumps in, from the point of view of the observer outside, this closed universe that is the black hole interior will not emerge. But from the point of view of the observer inside, using this observer rule, you would say that the interior or the closed universe is emergent. Okay, so this was the story, in the case of black hole evaporation. So now, sorry, this was a story for the tensor network. So now I just want to briefly end this talk by putting everything together into one proposal for covariant diagnosis. So what have we learned? What is spacetime emergence? Well, both the large N definition and the error correction definition that we talked about today are about consistency of a finite N picture with a putative approximate local picture in the bulk. What I mean by this is that the question is really to ask whether it becomes possible to find correlators in the fundamental description that are inconsistent with the existence of sub-exponentially complex local physics on a given spacetime at scales that are higher than the Planck scale. Okay, this is just like this. It's asking, I have my correlators. Can I detect that they're not the right ones if I want this geometry or not? Now, if an observer is added, the question is the same, but now the fundamental description also contains observer clone degrees of freedom, and the relevant scale is the observer's entropy, at least according to this observer rule proposal. The large N method is more precise, but it doesn't yet formulate emergence for quantum volatile spacetimes and polynomially complex operations, and so I think it would be really valuable to do so. And perhaps most importantly, it does not incorporate the analog of an observer rule yet, and I would say that it would probably be very insightful to really understand what an analog would be there. Maybe it's related to these filters that Hong was talking about yesterday. I'm not exactly sure at this stage. Okay, so now that we know what it means for spacetime to fail to emerge, when does such a failure happen? If I take a general spacetime, when will I have such a failure of emergence? Well, there's a suggestion from the two examples that we saw above, so the closed universe in the AS² geometry and the fully evaporated black hole, which is that the failure of emergence happens when there is a QES that satisfies certain properties in the geometry. The first property is that it's homologous to the boundary, or the boundary plus the observer clone, in the case of the presence of an observer. The second is that the holographic map factorizes into a tensor product across this QES. And the third one is that it has a very low generalized entropy for some semi-classical states in the code subspace. So here the examples of QES that appear in the case of the AS² cosmology are just the union of the two surfaces, the empty surfaces that separate the ADS regions from the closed universe. Those satisfy these three properties, and this is because the state psi1 that goes through has extremely small generalized entropy. In the same way, for the fully evaporated black hole, you can also consider a QES that essentially disconnects the interior from the exterior and the radiation at the singularity. So we will refer to such a QES as an evanescent QES because it's extremely small. It's almost not there. What we will propose in this upcoming work is that for general spacetimes, we can ask, given a spacetime, what is the largest region of these candidates that can emerge from a boundary description? And it seems that the answer, which we propose to call the complementarity wedge, is covariantly defined and always ends at such an evanescent QES. So stay tuned for the details. And how much time do I have left? Okay, yeah. Then I will just flash this as the complementarity wedges of the different examples. Thank you for your attention.
I have a couple of questions about your Noble theorem.
Mm-hmm.
So the first one is, and to understand one assumption is that there is a good larger limit for these states.
Sorry?
One assumption is that there is a good.
Yeah, the assumption is that there exists a large limit.
So how does that? So what's the relationship between that and yesterday's talk?
Yeah, good. Okay, in yesterday's talks, we learned that at least there are some arguments that make us believe that if we believe some things about the states, then we would conclude that they don't have a large N limit. My argument is saying, assume that they have a large N limit, then this large N limit cannot be a mixed state. So I think you can sort of see those two statements as, being two different ways of like getting stuck, right? Either you assume that there's a large N limit and then you find mixed state, or you assume that a mixed state is there and then you find that there's no large N limit. Either way, there cannot be a mixed state. That's the way I would say it. Yeah.
The question is, again, on the Noble theorem, does it apply to the case where you have large entanglement, say scaling with n entanglement?
Scaling with n entanglement? Good. So I think that's related to what I was saying about this polynomially complex operation business. So what Jonah was telling us yesterday is that if you have, for example, an entanglement that with a closed universe that scales with n, and you just look at this algebra generated by finitely many single trace operators, then at large n you would say that this algebra is in the mixed states. And this is because of this divergent entanglement. So from that point of view, the theorem would fail. However, I think that maybe another physical question to ask would be, well, how can we say in the language of that large n limit story how even in that case we would expect a swap test to be polynomially complex and still detect a failure of emergence? But I don't think it's completely clear how to formulate this in the large n picture, but I would like to do that. Yeah.
Yeah, thanks for a very nice talk. Can you go to the slide you had towards the beginning about like the definition of emergence?
Yes.
Yeah.
Oh, no, maybe not here. You want the large n definition, right?
Yeah.
Okay. Sorry.
Yeah, that's fine. Okay, good.
Oh, sorry. Yeah. Okay. Yes.
Yeah. So I have a couple of worries about this, and I'd love to know whether like you share the worries or whether you reassure me.
Okay.
The first, and they may seem to be the same worry. The first thing, which I think you mentioned later in the talk, is traditionally when we talked about bulk reconstruction, we said we only got to reconstruct correlation functions which didn't have so many like points in them that they caused back reaction, right? So only finite products. Of course, when you're taking the large n limit, there sort of isn't back reaction, and that's my second worry, which is that the geometry you have on like the next slide, right, where you inserted an operator and it caused a big crunch. Does that even make sense as n goes to infinity, right? Like I can insert the operator, gravity is still there, but it doesn't cause back reaction.
So this is not the operator. I'm not sure if I understand the question correctly, so tell me if I don't. But if I do, then the point is that it's really not the heavy operator that you're trying to reconstruct. It's the light fields that live on top of the putative background that would be created by the heavy operator.
But it would be created by the heavy operator in the small but finite n limit, right? Like if n was infinity, it wouldn't actually cause a closed universe to form, right? Because there's no back reaction.
Well, I mean, you can have, in the large n limit, you can have spacetimes that form that are not just empty ADS, right? Like, I'm not exactly sure how this would differ from the case of a long wormhole, for example, that you would have in the large n limit. There's no back reaction from the point of view of these finite single trace operators, but because this operator is heavy, it contributes to creating the large n background.
But heavy is itself, it seems like there's an order of limits thing here, right? Like heavy really means scaling with n, and as n goes to infinity, that's sort of a subtle thing.
Yeah, but the point is that the only things that I want to think of the limit of in this geometry are really the single trace operators. At no point am I trying to talk about the large n limit of the correlators of the heavy operator. I just want to talk about the large n limit of single trace operators, and the reason why I want to do that is that they would be light probes of your emergent geometry.
Do you maybe agree, like it seems like when we talk about gravity, we really mean large but finite n rather than infinite n.
Yeah, I think the question is I think the question that I was asking here is if you have a finite n picture, does there exist a picture, which could be the large n picture, if it's quantum volatile, it's more general, but some kind of effective picture that you can always map into the finite n picture up to exponentially small errors. So I think I'm still thinking at finite n from that perspective. Yeah.
Maybe just a comment related to that.
Yeah.
So when you introduced the code picture and you said that you want to preserve the inner product up to the minus n squared, you can't also say that the bottom half of the code is the infinite n theory. You need to include perturbative corrections.
Yeah, sorry, I was being a bit sloppy because, so what in the first definition of, algebraic large n limit way of thinking about things, usually we really think about it at n equals infinity. And this is why I just wrote a definition, actually it's here, that just is a limit. There's no constraint on how fast this limit goes. On the other hand, usually in the tensor network case, we think about a limit that goes exponentially fast. And this is because we want to think of this limit at containing perturbative corrections. Yeah.
Yeah, so then the other comment was if you can just show the tensor network for AS squared for a sec, I think this is
sorry.
Yeah, that's good. So the comment is another way to see. So you can see explicitly from this network that the state in the CFC has erratic n dependence, because if you just look at this network, it's preparing a pure state of A, but it's an O dependent pure state of A.
Yeah.
And O rho is something that, is very sensitively dependent on the UV structure
Yeah.
theory. So then you can see that this is, just from the picture, it's not going to be a state that has a large end limit.
Yeah, I think this is kind of mathematically the same argument as the thing that you would do when you compute the fluctuation of the inner product, but it's just the interpretation is also different. Like from this point of view, you can also see the interpretation as saying that the fluctuation is not so much the fact that the inner product is not preserved, but just inherently the fact that this operator O fluctuates between the different ends. Yeah.
Okay, for the sake of time, thank you for the time. Let's thank Elliott again.